let's review for the Unit 8 exam. And so the Unit 8 exam is basically on two topics: work and energy. Okay, and then conservation of mechanical energy. These two ideas. So, we have energy, the basic definition of energy. Now, I'm not going to write out all these definitions because you can write them out, and I don't have time. But energy is the capacity to make a change in the environment. And there are multiple ways that energy exists in nature. You hold if there's a rock at the top of a cliff, that rock can do work. I mean, it can do damage. It can make changes in the environment. It falls down. That's what we mean by gravitational potential energy. You have a hand grenade with a pin pulled. Okay, that hand grenade can do some serious, make some serious changes to its environment because there's energy stored in the way those atoms and molecules are arranged. When those atoms and molecules go through a very rapid chemical reaction, they will release energy into the environment. A moving train has energy. It can make change. You can just go, stand on the tracks and see what happens. Don't stand on the tracks. But obviously a moving train can, it's got energy sort of associated with it. So the first major idea we developed was the work energy theorem. And this is what we did. We took a crate and we just said, let it be at rest. Let there be a net force on it. And we'll just say that this is the net force on it. And we allowed this to go through some displacement, delta x. And what we found was when this cart was over here, we related the work that was done to how fast it was moving. Like if I apply a force through a displacement, and here's the definition for work. Work equals the force times the displacement. I'll call it delta R. R can be in any direction, but here delta x is obviously in the x direction, times the cosine of the angle between the force and the displacement. This is our definition for work. And what we're doing when we're doing work is we're transferring energy from one system into another system. Somebody's pushing on this cart. They've got energy in them. They're taking some of their energy and transferring it to this cart, and that's manifesting itself as kinetic energy. So this is the work done by that net force will result in the change in kinetic energy of that object. Now remember what we defined kinetic energy to be. Well, this is K final minus K initial. K final minus, this is 1/2 mv final squared minus 1/2 mv initial squared. Okay, so there will be problems where I'm going to give you the force on an object, and that'll be the net force acting on that object, and I'll ask for what is the final velocity? Well, you apply this equation right here. You just have to know what the bits and pieces are. Let's start here. And then say, okay, what is the net force? What is the displacement? Are they in the same direction? Are they in opposite directions? They're in opposite direction. The cosine of 180 is -1. That means we've done negative work. That means our force is slowing the object down. We're taking kinetic energy away. Remember that kinetic energy, that's the energy because an object is moving, can never be negative, right? 1/2 is a positive quantity. Mass is always positive, and if you square the velocity, that's always positive. But you can have a negative change in kinetic energy. If a car is moving down the highway and it's going really fast, it's got a lot of kinetic energy. You apply the brakes, you slow down, your kinetic energy is lost. You have a K final minus K initial gives you a negative quantity. That's a loss or a negative change in kinetic energy. Where did it go? It depends. If you're coasting up a hill, that kinetic energy became gravitational potential energy. If you're braking, your car brakes, regular car brakes, you're turning it into heat and dispersing all that energy into the environment. If you drive a hybrid or an electric vehicle, when you hit the brakes, some of the energy is turned into heat, but some of it is also used to generate electricity and store the energy in a battery. That's why hybrids are more efficient, because when they brake, they store that kinetic energy, like 80% of it gets put back into a battery. But anyway, this is the big idea, the work energy theorem. Make sure you understand units as well. What is work is measured? Well, this is a Newton times a meter. That's a joule. Newton times meter is a joule. And look at this. Does this come out to be joules? I'm saying, hey, if I do work, I'm going to change kinetic energy. Well, look at this. What is mass? Kilogram. What is velocity squared? Well, that's meters squared per second squared. Well, what's a Newton? A Newton is a kilogram meter per second squared, right? Mass times acceleration. That's what force is. Times a meter gives you meter squared. Kilogram meter squared per second squared. It's the same stuff. Okay? I do ask some question about units, so make sure you understand units. Okay? So this is the first major big idea, work, defining what work is, and the work energy theorem. If the net force is doing work, it is changing the kinetic energy of the object. That is a law of nature. Now, we have other ways of storing energy in the environment. If I've got the ground here, and I've got like a bowling ball way above the ground, well, gravity can pull it down like this, and I'm at a certain height, like this. So compared to this ground, I'm going to say this is my ground. This is where my gravitational potential energy will be equal to 0. Gravity can do this much work. mg times a downward displacement, well, that's work, isn't it? A force times a displacement. Gravitational potential energy is the work that gravity can do. Okay? So we say, hey, gravitational potential energy is equal to the weight, that's a force, times the height, that's a displacement. Now, what if you're down here at the bottom of a well? What if my bowling ball's down here? Well, how much gravitational potential energy does it have? Well, notice here that my height is going to be what? It's going to be a negative value. Unlike kinetic energy, 1f squared, everything there is positive. But here, okay, my weight, is good, but my height is negative. I'm below. So in other words, gravity, look, if gravity is like this, but you have to lift it up like this, notice that the force and the displacement are in opposite directions. So you have this mg times h times the cosine of 180 degrees. Well, that's -1. Or you can think, hey, you're below your reference point, so you have negative gravitational potential energy. Okay. So kinetic energy is always positive. You can have a negative change in kinetic energy. But gravitational potential energy can be negative, depending on where you put your reference. Now you could, if you're doing this problem, say, hey, I'm going to make u equals 0 right here. That's fine. You can change the reference of where you measure gravitational potential energy from anywhere you want, as long as you stay with that reference throughout the whole problem. In the middle of a problem, if you change where you measure gravitational potential energy from, well, you're magically creating energy or magically making energy disappear, which will magically make points disappear from your test. Okay? So once you pick a reference, stick with it. Which means that, the height of this bowling ball would be, this plus this now compared to this reference. Now, so we have gravitational potential energy, we have kinetic energy. We also have elastic potential energy. I don't have an equation for it, but it's just the energy stored in a stretched or compressed material, like a spring or a rubber band or a bungee cord, something like that. So energy can be stored that way as well. Like if you have a bow and arrow, you pull the bow back, you've stored energy and elastic potential energy, you fire it, it does work, and turns that energy into kinetic energy, and if you point it straight up, like an idiot, the arrow will rapidly go from kinetic energy, gravity will slow it down, it'll turn into gravitational potential energy, and then it will come back down with, kinetic energy again. And it will do work on, hopefully not on the top of your head. So if we have a situation, if and only if, have you seen IFF in math? If and only if the only forces doing work are gravity, the force of gravity, and or springs. And by springs, I mean a springy material, an elastic material. Then mechanical energy is conserved. And now, let's define mechanical energy. Mechanical energy, by definition, is when I take a look at an object and I say, is it moving? That's kinetic energy. Does it have height? That's gravitational potential energy. Is there a spring involved? That's elastic potential energy. Okay? So this defines what mechanical energy is. Now, you look at a system and you say, okay, if a spring is doing work, a spring is doing work, chances are you're transferring energy back and forth between kinetic energy and potential, elastic potential. If gravity is doing work, chances are you're exchanging energy like this, but you can also exchange energy. So if the only forces doing work are springs and energy, all you're doing is you're taking this energy and changing it into this or this into this or whatever. But when you add them all up, what do you get? You get this. You get what you started with. So in other words, the initial energy is equal to the final energy, which means now if you work a problem on the test, you go, okay, K initial plus U sub G initial plus U sub E initial equals K final plus UG final plus UE final. Now you might have a problem. Hey, look, initially it wasn't moving, and there's no spring in the problem. And at the end, I'm up a hill, so I still have some of this, and but I also have some kinetic energy. Now I'll go, okay, mgh initial equals 1/2 mv final squared plus mgh final. Now you've got an equation that you use the law of conservation of mechanical energy to construct, and now you can solve the problem. For example, on the test, you will have a roller coaster problem. Okay? And given energy here, energy here, energy here, maybe energy here, if you fall off a cliff, The only force doing work in this roller coaster is going to be gravity. And so you go E initial, we can call it E1, equals E2, equals E3, equals E4. And so you just set it up just like this, solve for the unknown. Make sense? The law of conservation of energy. It really works. Pardon the pun. Now, what if you do have friction in your problem? What if you do have something that's adding or taking away energy from your system? I might add, like in the typical problem I'm going to give you, very similar to the starter problem, and if I have a skier at the top of a hill, okay, and here they are. They got the poles. Okay, and they're going to go, oh, got to have a scarf. And they're going to go down the hill. What happens if they're going slower than they should? How much energy did they lose? Well, if you want to know how much energy they lost, that's delta E. Delta E is how much their mechanical energy changed. And that'll be E final minus E initial. Now, if they lost energy, they lost mechanical energy due to friction between their skis and the snow, what's going to be true about the value you're going to get? It's going to be negative. This will be like mgh. Maybe the skier was moving, plus 1/2 mv squared. This is going to be just like v, 1/2 mv squared. So this is 1/2 mv squared. This will be mgh. But this will be bigger than this. You'll get a negative value. You lost energy. If your delta E is negative, that just means you lost energy. You disperse mechanical energy into the environment. Okay? So there'll be a problem like that one. So here I'm looking at the test. There's multiple choice on this test. So make sure you understand that, hey, what happens if you double your velocity? What happens to your mechanical energy if you double your velocity? Well, what is 2v squared? Yeah. If you double your velocity, but remember, it's 1/2 m, twice the velocity squared. What is that? What is 2 squared? 4. You have 4 times the energy. If you want to go twice as fast, you have to do 4 times as much work to get an object up to speed. Kind of interesting. Let's see. Covered that. I think we've covered just about everything. Make sure you understand the units for work and energy and power. There are some power problems. Oh, I didn't mention power yet. Power equals the energy transferred divided by the time it took to transfer that power. So if I give you the power and I give you the time, you can figure out how much energy got transferred, how much work was done by the motor or whatever. Right? So, and this can be energy transferred, it can be work. Okay, I think we've covered it pretty well. All right, so come to class next time. We'll have the test next time. Be prepared to grade the take-home test at the beginning of class. We'll do that. Make sure your notebooks are ready to be graded. We'll grade them at the beginning of class next time. That is all.